Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video on math-based course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we jump into our sections 2.1 to 2.4 quiz in the Big Ideas Math Integrated Math 3 textbook. We're in things regarding linear and quadratic functions. We've also had absolute value, which I guess applies somewhat to linear. So 2.1 was transforming those, all of those ones, constant, linear, absolute value, and quadratic functions. 2.2 was linear and absolute value transformations. 2.3 was modeling with linear data. Actually, what was it? I think it was modeling with linear data. I'm always forgetful of what they all are. And 2.4 was solving linear systems. So, all told, we have those 4 and 13 questions to do so. I believe the quizzes break things down by section. They probably even go in order. So hopefully these 13 are a great comprehensive set of what we've done. If I feel like I have to teach more of what's involved in them, I will do so. But without further ado, we'll go ahead and check out what these ones look like. If you want to jump down the description section down below, you can find this PDF and download it. Especially when it comes to the quizzes and the reviews and such, they tend to be a little smaller in print. Maybe it's harder to see whether you're watching on your computer, phone, tablet, whatever it is. Always select that 1080p option if and whenever you can, like if you're able to, just to make sure that print comes out a little better. Otherwise, go ahead and download it and you have it, or you have access to the textbook itself. That's always helpful in these situations. Okay, and I will also, provide timestamps down below for each problem. We're obviously going to start with number 1, and graph paper. I'm going to provide graph paper for you in case we need it, because we might need it for numbers 1, 2, and 3. Let's see what's going on here. Let me get my thing up here. Okay, number 1, 2, and 3, identify the function family to which G belongs. Compare the graph of the function to the graph of its parent function. Let me actually do this as well. Give me one moment here. I'm going to copy and paste this, but I'm going to get a really high resolution version of it from my PDF instead of that thing you're looking at. So it's just going to look a little bit, whoa, that's pretty high res in comparison, a little bit better. So I won't use the graph paper. So sorry if you have to draw a graph for this yourself. I feel like you don't have to. I just want to draw the parent function in comparison to this one just so it's there. So number 1, we have g of x equals 1/3 x minus 1. We have to classify which thing this is out of. This is the linear function set. Now there are a couple ways that we can come up with what this is. Looking at the graph, we can see that it's just a line. The other versions of this are a horizontal line, which would be a constant function, otherwise a V shape, which is an absolute value function, and a U shape, which is a quadratic function. So this one's linear. The other one to this is there's no absolute value symbol, there's no squared, so it's to the first power, and there's an x there. If it was just like that, it would be a constant. So those are the two things that make this the linear case for that portion. Now they also say compare the graph of the function to the graph of its parent function. The parent function would just be some sort of f of x equals x, literally just the letter x. That means a slope of 1 and a y-intercept of 0, which would be going like this. This is the part that I actually wanted to draw. So right here, it would look like this in comparison. Now I don't need this drawing here. I just want to make sure that you're reminded of the different kinds of things that we mentioned. I also probably will mention domain and range and stuff. I don't know if that matters, but I'll probably do a couple of those things. Now, with this here, we compare it to it and we state, well, what did it do? It seemed to have compressed itself vertically, and that's where the 1/3 takes place, and it seems to have translated itself downwards, and that's what the -1 is doing there. When you ask, hey, what are you doing there? That's what it's doing. So to describe this stuff, I'm going to state those two things. I'm going to be vertically compressing this function, vertically compress by a factor of 1/3 is one of the things that's going on, and then also translate down 1 unit. Now those are the two things in comparison that I'd say that thing is doing. I don't know if that's exactly the way that they want those things to be described, but that's what I wanted to state on that as a whole. Now as far as domain and range go, the domain of this is all real numbers. The range of this is all real numbers. Linear functions will generally have that nature as long as it goes up and down forever and left and right forever. As I'm noticing right here, clearly I didn't give myself enough room because I made the graph way too big. So I'll make sure to not make it so big on the next question here. But that is number 1. Okay, that was a tight squeeze as I did all that. Let's go to number 2. Now on number 2, I'm going to once again do my copy-paste job, so give me a couple moments. I have a few windows open and I have to click from one to the next to do it. Let me first drag that over. Let me find my other window where I actually have number 2's graph. I'll copy and paste that, and I'll make sure to make it smaller. Not so much smaller, but a little smaller. Okay, number 2, what kind of function is this? You can either look at the equation or look at the graph itself, or a little bit of both. I'd say a little bit of both might apply here. Is that small enough for us? Let's see, I'd say so. All right, so number 2, just barely, because the equation's down there on the bottom. Let's do that. So number 2, we have g of x equals 2 times x plus 1 quantity squared, and it's U-shaped. This makes a quadratic function. I guess on the side, I might as well list domain and range. Let's look at the graph as far as how domain and range work. Most of these domains will be all real numbers. I'll just say they just pretty much will be. This graph goes forever left and right, but the range in this case is a little different. It doesn't go up and down forever. It actually has a limitation of how low it goes. The vertex down here is at a y value of 0. That is its minimum y value. So 0 is the lowest it goes, and it hits all the positive numbers thereafter. Y is greater than or equal to 0. That's how the domain and range works there. Now, I still have to describe the transformations, compare it to the function of its original parent function. And again, I don't know if domain and range is a requirement, but I am putting it. So let's talk about the couple things that it's doing compared to its parent function, beginning with that, because I want to graph the parent function. So the parent function f of x will just be x squared, which looks like this. Oh, these are going by 2's, by the way. This is 2, 4, 6, 8, 10, 12. So be very careful with that. Whereas these are just going by 1's. 1, 2, 3. I didn't notice that actually. So the original parent function, if you go over 1, you go up 1 squared, which is 1. You go over 2, you go up 2 squared, which is 4. Over 3, up 3 squared is 9. Over 4, up 4 squared is 16. Now that'd be 14. 16 is actually above that. So it'd be kind of like probably up there. Generally not something we'd plot, but I'm going to go ahead and do it anyway. So, and then I reflect these across this axis of symmetry. We'll talk more about that in a future section, or you probably remember that from IM2. And these kinds of things that I'm talking about, that 1, 1, 2, 4, 3, 9, 4, 16, those are things that I do in a tableless manner when I do my other graphs in general. I don't know if we have to graph any of those together on this quiz, but we did have to in the previous sections. This is section 2.1 we're talking about right now, by the way. And with this parent function, I want you to keep in mind that this is just a basic x squared function, first of all. Second of all, this graph is scaled by 2's on the y-axis, and it's scaled by 1's on the x-axis. But f of x equals x squared. How does this blue one compare? Now, this blue one is narrower. It's narrower than this one, which is wider, which, like I said, because the scale changes, it's generally not this wide, but it is narrower in comparison. And there's a translation. There's a translation 1 unit to the left of this thing. And that is all taking hold based off the two numbers, the 2 and the 1. Now, the 1... I got some sort of doorbell ring. Now the 1 is the translation, but you don't translate first, so to speak. You want to do the, I guess you can state it here first, but you want to talk about the stretches and compressions and reflections and stuff first, and then we want to talk about translation second. So the first thing we're going to say is we translate, excuse me, I just said we don't do that first. We vertically stretch by a factor of 2. And that's what's making it twice as tall, or really in your eyes maybe twice as narrow, but it's making it twice as tall. Everything here is, instead of going over 1 up 1, it's going over 1 up 2, stuff like that. Instead of over 2 up 4, it's over 2 up 8. And then you also translate 1 unit to the left. And those are the two things that's happening compared to the original function, the parent function. So that's number 2. Okay, number 3. Number 3 has a V-shaped graph. If we want to preview that beforehand, I still have to copy-paste it. So let me get that one in. But a V-shaped graph, and you can tell based on the function itself, there is an absolute value portion. This makes this an absolute value function. Now, what's happening in the function itself? Well, only time will tell on that. Let's take a look. I want to make sure the scale of the first one wasn't... Is this going to crash? Hold on. It's not letting me... Oh, my thing, I think, crashed. Give me 1 second here. Okay, I had to restore this thing. It crashed, so I just lost my previous 2 problems. It's fine for me. You have it on video. But yeah, I had to reopen this little binder paper side of things. So apologies. Some things happen. It happened when I was copying that other part, so it's likely that it just ran out of like memory or something like that, or RAM. I'm not really sure what was going on. So I don't know if this thing even copied. Let's see. I tried to hit copy. Good, it came in. So let me resize this thing. Apologies. You probably saw a quick flicker of losing that screen and duplicating that other one. Okay, so we're on number 3. We have this absolute value function, and let me go back to my page. Okay, so yes, absolute value. being the V shape and seeing the function for what it is. Let's still talk domain and range. Domain being all real numbers. Range being limited by y. Now, none of these were flipped over, so I guess we don't do anything with that. But this one's still upward. This is going by, yeah, ones and ones. All's good there. So this y value here is -2. That's the lowest that it goes. So y is greater than or equal to -2 in that case. That's as low as it goes, and it goes up from there forever. Now, when we talk about transformations, we compare it to the original absolute value function, which would have looked like y equals absolute value of x. It would have just gone over 1 up 1, like so. But on the other side, it would v off and go like this as well. Probably about right there and then right there. So this absolute value function would be looking like this guy here. And this one's nice as far as comparing to, because it doesn't look like there's a change in stretch factor. It's just translation change, which means I can do a translation change to show you exactly how this thing would map onto it. Exactly. So with this one here, I could literally take this and translate it 1 unit left and 2 units down, and then you can see it goes right on there. There's no other vertical stretch or compression. There's no reflection of this thing. It doesn't flip over an axis. So we can just describe it by those two things. We can translate 1 unit left and 2 units down. And that's how it compares to the original f of x, if you will. That's how g of x is. And that is showing up in the equation as well. I don't know how much I've been making mention. I don't know how much I've been making mention of the original equation here, but that one's absolute value of x plus 1 and -2. You probably know the effect of that vertex form. +1 means 1 to the left, and then the -2 is the 2 down, that kind of thing. Okay, let's move on to numbers 4 through 6. This is still part of section 2.1. Graph the function and its parent function, then describe the transformations. And, well, I guess it's a lot like these other ones. Maybe this time I'll not do domain and range, and hopefully there's some that get flipped over and such. So use this graph paper as you will when it comes to the problems. I'm going to copy and paste that guy in. Let's get it ready. Let's get it a little smaller like that. That's good. Oh, that's good. That's good. Normally, I think on this section itself, I had the parent functions kind of locked and ready to go, but that was because we had so many problems to do it with. This time we have 3 of them. We have a linear function on 4. We have an absolute value function on 5, and we have a quadratic function on 6. So they're really staying away from the constant functions. They don't care as much about those because they're not so diverse. So this one is f of x equals 3x. Now that is actually the transformed function. Let's start with the parent function, y equals x, and I kind of showed that one before. It's just an up 1 over 1 bit like this. And we'll compare this one to that one. And it just uses that single number. I think we can visually represent as well. But that 3, as I start graphing this one early on, that 3 is a number that's more than 1. That 3 is multiplying by x, not adding to it. So it's a representation of a vertical stretch. Because it's more than 1, it's a stretch, and we're going to see that right here. Now, there's no translation. There's no y-intercept change. It's just 3x. So we go up 3 over 1 instead of the up 1 over 1 that the original graph had. Now, this one also doesn't reflect. It's still going up and to the right, down and to the left. That makes it a positive slope. But this one is vertically stretched in comparison. By what factor? Well, factor of 3. Everything is 3 times taller than it was before. I don't like to call it skinnier so much, but it is taller. So it's vertically stretched by a factor of 3. So there's the graph. There's its parent function, the original one in black. And then there's the description on 4. That's all I'll do for these ones. And I got to kind of talk over what I'm doing as I do the rest of the graph there. Okay, number 5. Let's get the paste job in first. Okay, number 5. We got f of x equals negative absolute value of x plus 2 minus 7. Like so. Okay. Now, we're comparing to the original absolute value of x graph to remind you of what that's like. That's just an up 1 over 1 thing like the previous one. It looks linear-esque, but at the origin is a vertex, and it does bounce off of that. And the reason for this, I mean, I want you to think of this in a table format, because I'm not going to graph this one using a table, but I want you to get the idea. When you take absolute values of positive numbers, you get positive numbers. Absolute value of 1 is 1, absolute value of 5 is 5. But when you take the absolute value of a negative number, you too get a positive number. Absolute value of -1 is 1. Absolute value of -7 is 7. That's why these things go up and bounce off like that, because y equals the absolute value of x. It's the same as the x value, just the absolute value. So it does maintain positivity on y. That's why the range is y is greater than or equal to 0. Absolute value of 0, by the way, is 0. Now this graph here does have a few components. Number one, if you know anything about vertex form, it's you flip this sign, it's a -2, you go 2 to the left, and then 7 down. I kind of brought that up before. This graph is not going to reveal itself too much, unfortunately, though, because this is also negative, which is the first thing we would actually tend to care about. That's the flip over thing. So this thing does flip over here. You know, you can use a table for this stuff. I believe that's something that the book really heavily emphasizes. Your teacher might as well. Or you can use a graphing calculator. And like I stated, I won't really go too deep into these. It's something where this is IM3 stuff right now. I graphed this in the very first section of IM2 without a table. So if you want to go back to section 1.1 in my IM2 playlist, you can go ahead and check out how I'm actually doing this. But it's use of vertex form, where that +2 means you got to plug in x values that are 2 smaller than you normally would. If I build a table around this, I'd put -2 in the middle of it, and I'd build around that to get these other points that I'm getting. Now the -7 means the y values will be shifted down 7 units from here. I think we're going to talk about this more in the section 2.2 stuff. But the flip over thing is actually technically the first thing that happens. This negative is a -1, and all your absolute value things that would have been positive, 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 now become negative, negative, negative. That's why it flips over that way, and then we translate. So there are two different, well, technically 3 different things that we mentioned, but the first one's a reflection. We reflect over the x-axis, or it's a reflection in the x-axis. And then we also translate 2 units left and 7 units down. Where's 7? So those are the 2 things that we describe with that. Normally I'd say g of x is a translation in this of f of x, but this one's called f of x, so I'll just leave it. And that's number 5. Okay, number 6, f of x equals 1/4 x squared plus 1. Now, it's daring when it comes to having the fraction, the 1/4 fraction, stretch factor or compression factor this time. But I am going to keep the scale factor the exact same, I'm going to keep the scales of these axes the exact same as they are, so I don't have to change anything or confuse you with it. I will have the original parent function popping up here in just a moment. So let's graph the original. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And there's a reflection on the other side. Just like absolute values, squaring negative numbers turns them positive. So the only thing that'll make this graph flip over is if there's a negative in the stretch factor, in what would be considered the a value. And this one is, well, first of all, this is the original parent function, which has a stretch factor of 1, which means there's no change on it. But even my new function right here has a positive 1, which means it's going to go upwards. But I'm going to begin with the vertex portion, shift the y values up 1 unit each, and get everything in relation to that. This is my new vertex. And I'm going to take 1/4 the heights of everything here. Instead of going over 1 up 1, over 2 up 4, over 3 up 9, I'm going to divide all those upness values by 4. This is a vertical compression. So instead of over 1 up 1, it's over 1 up 1/4. And it almost looks like it's supposed to be hitting that graph. It's just that my graph is so thick you can't tell where those points are. Instead of over 2 up 4, I'm going to go over 2 up 1/4 of 4, which is 1. And I'll do it on both sides here. Remember, squaring -2 is still positive 4, but now it becomes a 1. Over 3 up 9. 9 divided by 4 is 2 1/4. Maybe you want to skip those ones if you're not sure what to do, but you can go by evens. And I always plot as many points as I can fit. So over 4 up 1/4 of 16, which is 1, 2, 3, 4. And once again, this is something you can do with a table or graphing calculator. I'm just giving you the know-how of doing it without it. Over 5 up 1/4 of 25, which is 6 1/4. 1, 2, 3, 4, 5, 6 1/4. And I'm going to fit one more here. Instead of over 6 up 36, we're going to go over 6 up 9. 36 divided by 4 is 9. And 9 up from 1 is at y equals 10. So this is a nice fatter graph which I can fit and draw very smoothly. What I like to say on these ones here, even though it's a fraction, a little more complex, is I like the character that this graph shows. You can see a lot of that curve shape on this if I draw it well enough, and there's no guarantee that I will. So there is the appearance of that quadratic function. So 2 things happen. You can tell both of them, hopefully. The vertex has a translation up, but before that, technically, there was the vertical compression, right? I did everything in relation to my vertex, but everything was vertically compressed by a factor of 1/4. So vertically compress by a factor of 1/4. That's the first part. 1/4 is less than 1. And then we translate up 1 unit. And those are the two things that occur there on the graphs. And hopefully you understand why I do this without a table, or how I can best those with the table, doing that in pretty fast fashion, even if I'm talking over it. Like, even if I have to spend the time to talk about it, I probably still beat those with a table who are crunching numbers in their calculator, probably going divided by 4. This is 0.25. If you're well versed in your numbers, you'll be better off this way. Now, maybe you're not. Maybe the solution guide video doesn't help you in that way, but here on out, I say here on out as in this is still early on in IM3 stuff. Don't expect me to do table-based graphing. I almost always will not. So if that's not for you, then I apologize. If it is for you, awesome. I'm glad you're following along. Okay, we're going to section 2.2, and we have numbers 7 and 8, where we have to write a function g whose graph represents the indicated transformations of the graph of f. Let me go on to the next page and see what they're talking about. I don't think we're graphing. We could, but we have f of x equals 2x plus 1. That looks like a linear function. Oh, and we are going to translate, I remember these. We're going to translate 3 units up. So now our g of x is going to be taking the f of x and doing this thing with it. And there are a lot of ways you can get this one done. Some are more simplistic, some are more rote with the way that the book would do it, which is g of x is the same as f of x, but it's 3 up. And where you see those events happen are outside of the function itself. You take the function and you add 3. That affects your y values. Up is y. This is the y effect. So you take your f of x, which is 2x plus 1, and you're going to add 3 to that. Hopefully that makes sense as far as what I'm saying there. That 2x plus 1 is f of x plus 3, and 1 plus 3 is 4. So g of x equals 2x plus 4. Now, they're not saying anything like confirm graphically whether this is true or not, but if you want to take on that appearance, 2x plus 1 would be a y-intercept of 1 and then a slope of 2 like that. And then 2x plus 4 is a y-intercept of 4 and a slope of 2 like that. And the comparison from one to the other is, hey, this is 3 bigger, 3 up from what it was before. That's just the appearance of what that thing is in number 7. I think that's all that's being asked, so I'm going to move on to number 8. Number 8 is f of x. Now, you'll notice the original f of x is not the parent function this time. We're not comparing 2x plus 4 to x. We're comparing it to 2x plus 1, because that was the original problem. Same with on number 8. This is not the absolute value of x that we start with. It's negative 3 times the absolute value of x minus 4. And we're going to do a vertical shrink, I call it compression, vertically compress by a factor of 1/2. So that's a vertically compressed factor of 1/2. Let's move this one whole thing down there. There we go. Okay, so g of x is going to take this thing and vertically compress it. Now, like I stated before, and it doesn't sound like, oh, we're going all the way to number 10 here. Awesome. Or number 9 at least. It sounds like here is another affect your y values. It's a vertical change in this. So we take our f of x, whatever it was before, and we're going to multiply that by 1/2. Excuse me. The shrink doesn't mean division ultimately if that number's already that fraction. We're still going to multiply by it, but affecting something outside vertically is affects it vertically. So we're going to multiply 1/2 by that entire thing. Now, the entire quantity is just kind of one term in and of itself, which means it only affects one part of it. So the 1/2 multiplies by negative 3, right? That's the only part that we actually change. So it becomes negative 3/2 times absolute value of x minus 4. Now, this is the simplified appearance of the g of x function. And I'll tell you what, I haven't done number 9 yet, but we've seen a lot more complicated ones in the problem sets themselves. We do a lot more. So if you want to see more, I don't know what number 9 will do yet. It has a lot more descriptors, so maybe. There's a lot, but if you want to see a lot more problems like this, definitely check out the 2.2 section that has these kinds of ones. Now, they don't say describe these, right? They just say write the function. Okay, we don't describe it. It's already described right there. That is the simplified function. Now, in comparison of one versus the other, this x minus 4 hasn't changed here, and it shouldn't change, but this is the vertex of the original. This goes down 3 over 1 and down 3 over 1. It's a pretty sharp downward turn, whereas this one is half of that. It's down 3 over 2, down 3 over 2, so now it looks like that. So it's the same graph as the other one when it comes to vertex, and it vertically compresses closer to the x-axis that way by being half the size as it was before. That's how those two would compare. And it's flipped over. Okay, number 9. This does look like the parent function, f of x equals absolute value of x, and we're going to do several things to it. So that'll be nice to compare to the parent function for one of these. So absolute value of x here, and we're going to do the following, and we have to do it in the specific order. Reflection in the x-axis, reflect x-axis, vertical stretch by factor of 4, VSF of 4, followed by a translation 7 units down, translate 7 down, and 1 unit right. Now, as I've stated, the book does do a lot more with these things. They've talked about horizontal stretches and compressions, which are a little bit backwards from the vertical ones. I'll only explain it if it pops up. Otherwise, I'll kind of leave it be. Maybe it comes up in number 10. I don't know. And sometimes it does things in different orders. Sometimes it'll translate first before doing the vertical stretch, and it changes your order of operations. It requires you to do parentheses in a different way. So I'll do it kind of in book form of what you do here, unless you totally know of what would go on. Let me write the final answer as I would tend to do it to begin with. This g of x is going to be reflection in the x-axis means you make the a value negative, vertically stretched by a factor of 4, the a is a 4. And then 1 to the right is inside of the function itself. This is where you'll have an x minus 1. That's where you have an opposite effect, just like horizontal stretches and compressions. And 7 down is also 7 on the outside that's subtracted. So this will be the final answer. But how do we get to that final answer as a whole? Let me turn it to black and move it down and just kind of hide it out of the way. All right, how do we get to that final answer? Let's start with some h of x here. The h of x is going to just be the reflecting across the x-axis. That takes your f of x and it makes it negative. You apply that, and that's where we get h of x equals negative absolute value of x. So that's a first component to this. A second component to this is a vertical stretch by a factor of 4, where you take your newly transformed function and you make it 4 times bigger on y. So let me actually move this up to fit some more stuff. So let's call this j of x, if you will. J of x is going to take your h of x and it's going to make it 4 times bigger in this way. So your h of x being negative absolute value of x, 4 times negative 1 is negative 4. So you get now negative 4 times absolute value of x. I know this is a little rote and mundane of what we're doing, but that's okay. Next one is, let's do k of x. How about that? K of x takes your j of x and it does a couple of things. 7 units down, actually let's start with the 1 unit right. 1 unit right, doing something horizontally is inside the function itself, inside the j of x. This is where the x minus 1 takes hold. This is where we're going to substitute x minus 1 anytime that we see x in this thing. The 7 down happens on the outside of this. This is the effect right here and do minus 7. Again, 1 right means we need to make the x's 1 bigger, so we need to counter that by subtracting 1 from these things to make that happen. That's why we swap it. So we'll take that j of x, which is negative 4 times the absolute value of x. So the function, negative 4 times x, is going to be replaced with x minus 1. That's what we do there. And then minus 7 will take effect in this whole thing. We're going to subtract 7 from that. And that's where we get the final answer, which is g of x. I guess I could have called this k of x a g of x, actually, because that will be the final. Because we are done with what we're doing. And that's where we got the negative 4 times x minus 1 minus 7. So a lot to be had there. You can do it one at a time. You can do it like I did all at once. Maybe it takes a little bit of practice to do, or maybe you really know how these transformations work as a whole. I'm sure this isn't the last time we're going to see transformations. Expect a lot more of this because this was section 2.2 on linear and absolute value functions. Section 2.5 should exhibit more of the same for the quadratics. That's why we didn't see a quadratic here. But note, we didn't see any horizontal compressions or stretches. I think they were nice with you on this. Expect some of those on a quiz of your own for your own classes. So definitely go back to the 2.2 stuff, look at questions like that and see what happens on those because they are massive descriptions that I have on them. Okay, let's go to number 10. It's still within the same section, but I think it's a different kind of question. Let's see. The total cost of an annual pass plus camping for X days in a national park can be modeled by the function f of x equals 20x plus 80. Noted. Senior citizens pay half this price. Oh, it is still some of the function transformations. Senior citizens pay half this price and receive an additional $30 discount. Describe how to transform the graph of f to model the total cost for a senior citizen. What is the total cost for a senior citizen to go camping for 3 days? Okay, so there are a couple things that we can do here. Let's begin with the description. Then we'll algebraically make a g of x transformation, and then we'll substitute something based on the 3 days bit. If x is the number of days, yep, x days, then we can do that for x. So let's begin with this. They do state that senior citizens pay half this price. Now, the only part I don't know is the 80 part. When I see the 20, it says the total cost of an annual pass plus camping for X days. The 20 to me represents you pay $20 per day. The $80 is an upfront cost. That's the annual pass. Okay, the annual pass plus camping. So you pay $80 for the annual. It says senior citizens pay half this price. So I assume they're paying half the 80 as well as half that 20. I know they're paying half the 20. They're paying $10 a day. But it sounds like it's also half the 80, which is 40. Anyway, you take. So G is a vertical compression of F by a factor of 1/2. That's where you're getting half off. Now the difference here is that we're not just taking half of 20, we're also taking half of 80. We're taking half of F. That's where this is going to be a little bit different from some of the other problems. So it's not just a vertical compression of the entire, of just the slope. And a translation of this thing, because it's a $30 discount, that means that they're paying $30 less than this thing overall. So I got to really think about still whether or not you're taking half of the 80 to make 40, or whether you're taking, let me think about it. Let me really think about this, because if you, yeah, I think you're taking half the 80, which is also 40. So, and it's a translation 30 units down from that, right? That's where that's going to be affected. So, sorry for the long description. I really had to process this myself to make sure that it makes sense to what we're going to do. So g of x is going to be this. Take a look. We're going to be taking half of f of x, the entire thing, right? This is affecting our y's. This is affecting our cost. Not the days, but the cost. And we're taking 30 away from that whole thing. So when we do that f of x bit, we're doing 1/2 of 20x plus 80. And then subtracting 30 from that. Not just half of 20, but also half of 80. So 1/2 times 20 is 10. And 1/2 times 80 is 40. Which will be 10x plus 10. So this is the function for senior citizens. What a discount. What a discount. Okay, now we are also going to find the cost for a senior citizen to go camping for 3 days. That's where we're going to do g of 3. That's 10 times 3 plus 10, which is 30 plus 10, or $40. $40 for 3 days. 3 days. So we use that function, we substitute that in, and that's what we should get from there. Okay, let's jump to, I lost my page. Let's jump to numbers 11 and 12 for section 2.3. 2.3 was modeling with linear functions. Write an equation of the line and interpret the slope and y-intercept. Okay. I think I want to copy and paste this guy as well. Let's get the high-res one that I can get again. Hopefully nothing crashes this time. Okay, here we go. So with this section, we sometimes use slope-intercept form or point-slope form. It's very good IM1 or Algebra 1 material that you're basing this stuff off of, which is nice. And the interpretation is just, what does the rise over run represent? So on number 11, write the equation of the line. Now, they do give you 2 points, but they also distinctly give you that this thing's going from the origin, which means I'm going to base this thing in slope-intercept form. I already know that my b value is 0 for y equals mx plus b. My slope is my rise over run of any 2 values which I'd like to choose. I can either rise here and run here. Heck, I can rise here and run here if I want to, and I'll show you that they're the same thing. Rise from 0 to 400 is 400. Rise from a run from 0 to 2 is 2. So going up 400 over 2, which is 200. You want to check and see if this works the same? We go from 400 to 600. That's a rise of 200. but now you run from 2 to 3, which is 1, and 200 over 1 is still 200. So the slope is 200, the y-intercept is 0. This equation is y equals 200x plus 0, or just y equals 200x. Now, x represents the number of weeks, y represents the balance in dollars. This is for a bank account. So we have to interpret the slope and the y-intercept of this thing. So the slope interpretation is simply, let's see, maybe I'll fit this on the bottom. The slope of this thing is the rise over run nature of it. That is, every week, your bank account, I guess ours, your bank account increases by $200. $200 every 1 week, right? You think of slope as a fraction, so it's 200 over 1, and that's where that one comes in. So that's our slope. Our y-intercept is 0, which means at week 0, when we started, or opened the bank account, or whatever, when we started our bank account, we had $0 in it. So basically, that's the start thing, right? You could start with $300. I want to open this bank account, put $300 down, awesome, and then add 200 each week from that, then it would be up here. It would be a vertical translation like that. This one's a little different, it doesn't have that. All right, there's number 11. Let's go to number 12. Give me time to do some copy-paste stuff, and we can probably talk about it. As we go to number 13 is the last one afterward. Keep in mind that's out of section 2.4. So let me just verbally talk about what this section also had in it as I get this copy-paste stuff ready to go. This section was heavily also involved in what are called scatterplots. And I don't suppose this is technically the same thing. Oh, I think this crashed again. Oh well, just give it a sec. Watch this. Just goes away and it does this. So I'll just keep this live as I reopen this. This is every time I'm copying one of those big things there. So I probably just lost everything before that. Apologies. I got to reopen my binder paper page. Anyway, now I get to talk through what the heck's happening, and you get to see the process of what I have to do on this thing each time and why it gets a little messy. I'm just glad it's not crashing my video recording and coding. If it did that, I would flip. Hold on. That's not what I'm trying to get. All right. So right here. Let's go to, did it copy? All right, it did. This section included, yikes, scatterplots. Scatterplots are big amounts of data, perhaps, a sample of data, which is, I can't talk and write at the same time, which can be all over the place. It can be like here, you know, like that. And what we do is we come up with a trend line for the data. Maybe it goes through that data stuff there. So if you want to see more things in section 2.3 like that, we have to construct what are called lines of best fit. We have to find what are called the correlation coefficient and using linear regression to come up with slopes and y-intercepts and stuff like that. So that's not on these questions here, unfortunately. I don't have any record of that for these ones. But let's do the same thing. Let's come up with slope-intercept form for this one. And I really will do slope-intercept form once again, because we also did point-slope form in the section. But I do see a y-intercept of 50. So my b value is 50. They're showing you the fall and the run on this one. These are both, well, these are scaled by 5s. These are scaled by 10. So be very careful if we talk about any of those in that way. Is that purple? Give me a second. So the slope is a fall of 10, noted in red, with a run of 20, which is negative 1/2. We can either write it as negative 1/2 or negative 0.5. It depends on what we're going to be talking about for the problem. So one version of the equation could be y equals negative 1/2 x plus 50, or we can write y equals negative 0.5 x plus 50. It really depends on what we're talking about. Let's see what this is. Shoe sales. A percent discount as well as price of pair of shoes in dollars. So the percent is like 10%, 20%, etc. I'm probably going to be doing this one here. Otherwise, this is talking about $0.50 for every percent. I guess that works. You can describe either or here. Let me actually do both. Let's just interpret it either way. So the slope interpretation can either be for every dollar, I'm going to do the fraction one first. For every dollar, the price of let's see, the price of shoes goes down. Let's see. Percent discount is the cause for the effect. For every 2%, this is the run, for every 2% discount added to your shoe cost, your price of pair of shoes goes down $1. You could also say, I'll just say this one out loud, because this is negative 0.5 over 1, so that's for every 1% discount added, your price of pair of shoes goes down 50 cents. Right, that would be the same thing, leaving it as the fraction or otherwise. So this is run and then rise that I mentioned there. Now the y-intercept says 50. 50 what? $50 for a 0% discount. So a pair of shoes without any discount, percent discount, costs $50. So starting from 50, when you start to get percentage discounts all the way to 100%, which makes it a $0 pair of shoes, yeah, it starts to lower when that thing works. So it's really a cause and effect thing. All right, that's number 12, but that's clearly not everything that we do in that section. I want you to keep this in mind. So this review isn't fully comprehensive, right? It's not fully everything that we cover under the sun, which is okay, but I want to let you know what's there that you got to check out if you haven't done so yet. And you probably have, but I want to remind you of those things because this quiz review is not necessarily indicative of whatever quiz you have, right? As this is just halfway through the chapter. Okay, number 13. This is out of section 2.4. This was systems of equations, solving linear systems. A bakery sells donuts, muffins, and bagels. The bakery makes 3 times as many donuts as bagels. The bakery earns a total of $150 when all 130 baked items in stock are sold. How many of each item are in stock? Justify your answer. Donuts cost $1 each, muffins $2.50 each, bagels $1.20 each. Okay, here is my plan. First of all, we don't know how many of each are sold. We are going to do systems of equations here. I'm going to use, and normally I wouldn't do this, but I feel like I kind of want to this time because D, M, and B are fine letters to not confuse with numbers. So I'm going to let D equal the number of donuts sold. Okay, don't need a period there. Let's let M equal number of muffins sold. And B equal number of number of bagels sold. I was thinking bakery. Number of bagels sold. So we have 3 variables. That means we need at least 3 equations to come up with a unique solution to this system. And I believe we have enough information for all 3 things. First one I actually want to do is just the total number of baked items. There are D number of, sold. There are D amounts of donuts, M amounts of muffins, and B amounts of bagels. And when you total them, you get 130 total items. The price for all of these, or when they earn a total of $150 here, comes from the cost per donut. There's $1 per donut times the cost of donuts, or times the number of donuts, plus $1.50 per muffin times the number of muffins. Hopefully you understand why I don't need the extra 0. Plus $1.20 per bagel times the number of bagels. And total, we get $150. Doesn't really seem like much increase, but when you consider nothing's, $2 or more, I guess it kind of makes sense. They probably sold a lot of donuts as well. And then the last one was actually the first thing they mentioned. The bakery makes 3 times as many donuts as bagels. So however many donuts they made, you got to take the number of bagels and triple it, right? The number of donuts is 3 times the number of bagels. That's kind of what we're looking at right there. Now, with all this is our system of 3 equations, and we got to solve this system. And generally, we would find some sort of method of solving. We can use elimination, but I'm going to go with substitution because I have this D equals 3B. I can take 3B and substitute it in for D in this and this right here. And by the way, 1D just means D, so I'm going to get rid of that one. So I'm going to substitute 3B into there, and it turns my system of 3 into a system of 2. It gets rid of the D's in these 2 equations. Equation number 1 now looks like 3B plus M plus B equals 130, and 3B plus B is 4B, so M plus 4B equals 130. Is that equation 1? And equation 2, I can rewrite now as 3B plus 1.5M plus 1.2B equals 150, or 1.5m plus 4.2b equals 150. Now, personally, I'm not a fan of having decimals in these things, so I'd rather multiply by some number that will get rid of the decimals. I guess by 10. There might be something smaller. I don't know for sure, so I don't think so. So I'm going to multiply everything here by 10 times 10, and I think I'll be able to reduce after that. This is something that I did quite often in my systems of equation stuff. That's why it was a 3+ hour video. 15m plus 42b. Actually, that's not why it was, but it was me making numbers better than worse. These can divide by 3, right? Divide by 3. Let's just make them smaller as I can. And this will become 5m plus 14b equals 500. And I think that's the least that I can do with that thing. So I now have two different equations, right? I have 5m plus 14b equals 500, which, by the way, contextually means nothing to us now that we've done some multiplication and stuff, but it still satisfies our system. And I have this other one, which was m plus 4b equals 130. So this is our new system where we get to solve for m and b, and I think that just not having decimals makes this a lot cleaner and a lot better looking for what we're going to do. I'm going to go ahead, and I just showed you substitution previously. Now let's show you some elimination. Let's go ahead and solve for m by multiplying this equation now by -5. If I multiply by -5, it will eliminate, so -5m minus 20b equals -650. It'll eliminate my m variable, so I can use that to solve for b in this case. 5m minus 5m is 0. Then you have 14b minus 20b, which is -6b, and 500 minus 650 is -150. You divide by -6, you get b equals 25, I think. Okay, so 25. That means 25 bagels were sold in total. 25 bagels were sold. Now I can use this information to find a couple other things. I can find number of donuts, don't forget, it's 3 times the number of bagels, and I can find the number of muffins based off this information here. So I have a couple equations I can revert back to. Let's go to this one right here. I'm going to bring it down. M plus 4b equals 130. M plus 4b equals 130. That's m plus 100 equals 130, or m equals 30. So 30 muffins were sold. And then I also have number of donuts by being 3 times number of bagels. That's D, number of donuts equals 3 times number of bagels. There are a lot of different ways you could do it, right? I could plug 25 and 30 into this original top equation as well. But number of donuts seems like the most. I expected that. By the way, it weighed itself down as 75. So normally we'd write the final solution as an ordered triple. But because it's a word problem, we can actually contextualize this thing and say there were 75 donuts sold, 30 muffins sold, and 25 bagels sold. And that would be our final answer. Now, it's something you could also double check. I'm going to trust that that answer is correct, but you can multiply 75 donuts by $1, which is 75 bucks. 30 times the 150. Actually, let me try this. 30 times 150 per is $45. So 75 plus 45 is $120. And then 25 bagels sold times $1.20 each is $30. So what was my other number? I said, what was my other number? 120. 120 plus 30 is 150, and $150 were it. And I think everything else falls into line. 75 plus 30 is 105, plus 25 is 130, 130 total baked items were sold. Okay, that's that final answer. That's the system that I worked off of to build it and solve it. So guys, that's the last question here. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Apologies for some of the glitches and crashes with this thing. I hope everything else was smooth along the way. And sorry again for the quiz not necessarily setting up every type of question under the sun. I know it couldn't. I like that the last one was a word problem to go off of. But outside of that, definitely check up on things like horizontal stretches and compressions. Definitely on section 2.2. Definitely check up on things like scatterplots, linear regression, things like that. Maybe you won't be quizzed on that if you're not expected to use a graphing calculator in any sort of way. But guys, otherwise, thank you. Take care. I'll see you in the next one.